Welcome to AI for Good, the leading action-oriented, global and inclusive.
Luis, you can go ahead. We had an issue with our video, so please go ahead. Thank you.
All right, that happens. Welcome, everyone. Thank you all for taking the time to join. Thank you to Marzyeh for taking the time and ITU staff for hosting us. So my name is Luis. I'm an ML researcher based at Fraunhofer HHI in Berlin. And yeah, I have the pleasure introducing Marzyeh today and trying to moderate the discussion a bit later. So I'm sure most of you know Marzyeh and her work. She is an assistant professor at MIT working in the space of machine learning for health. And I mean, her receipts are numerous. She publishes in major ML conferences. She has a lot of work with clinical partners across different stakeholders and is one of the founders of Ali, a new organization that tries to advance the research and practice of machine learning for health. So yeah, we have the pleasure of having her with us today to talk about designing machine learning for health systems in an equitable way. And we will first have a presentation by Professor Ghassemi, and then later we'll follow up with a discussion at the end. So Marzyeh, I give the floor to you and looking forward to the presentation.
Thank you. All right. Great. So thank you, everyone. Today I'm going to talk about designing machine learning processes for equitable health systems. And as we said, I'm Marzyeh Ghassemi, and I am at MIT in IMS and EACS. And the thing that I think we should frame the rest of the talk with, and something I'll come back to at the end, is the fact that all of the data that we're working with in a health context is embodied data. It's data from human bodies. And I will argue throughout that robust, private, and fair algorithms require diverse data sets for research use. Current medical harm and inefficiency can't be addressed by just applying a naive model to some small subset of data. If we want AI to improve science and address medical harm, we need better data. My lab focuses on creating actionable insights in human health. We call ourselves the Healthy ML Lab. And I'm going to talk to you a little bit about my research today, and then I'll, the technical parts of it, and then I'll up-level it a little bit. So first we'll talk about how you design healthy models that are technically sound, but we'll also talk about how we audit healthcare systems to make sure that the practice that is being done is working well for everyone, and then how we deploy systems in a way that improves behavior of clinicians. Let's pretend we have a patient, Sumana, who's having trouble breathing. What happens is she'll come into an intensive care unit and it'll look a little bit like this. We'll have her EHR data. And the standard setup in machine learning problems that you may have seen is something like this. We observe patient data. You have vitals and labs that are changing over time, maybe irregularly sampled or noisy. And then we want to play the patient's record forward to our neural network and score the neural network on whether it has real-time prediction. I mean, it's not actually deployed in a hospital, but we're viewing a record as if little pieces of it are coming in at certain times. And we try to predict whether somebody needs a drug, whether they're at high risk for mortality, whether they're developing some condition by some gap time before a clinician was observed to act on this patient in real life. So this is the standard learning setup. And here's one example of something we did. This is a few years ago now. We took 34,000 ICU patients from the Mimic-3 dataset. That includes static variables, time varying vitals and labs, things like oxygen saturation and lactate levels. And we take all of the clinical notes for each patient in every stay. We pre-process them with a topic model, another kind of machine learning model that turns variable length notes into a vector of numbers of the representation what your note was mostly about. Maybe one note is mostly about critical care, 70%, and then 30% about oxygenation. And now that everything is just a matrix of numbers, we can concatenate these variables over time so that one patient is a set of variables over a set of hours. And that's great because now when we think about expanding that across a whole hospital, we have a tensor of data. And with the tensor of data, we can learn in many ways. I'm going to take you briefly through one paper's results where we used a recurrent neural network. And here we found that by representing data in intelligent ways, here it's the way I described, where you have missingness represented in this tensor of data that patients are observed under, we get better performance across a really large range of tasks. So here we're not tuning one bespoke model for every single intervention. We're allowing the model to perform on all tasks to see how well it can do. And we find that for things like invasive ventilation, non-invasive ventilation, and then vasopressor administration, that's a drug that keeps your blood pressure up. And then whether we give you a fluid bolus or not, you really see better performance in deep models if you represent data intelligently. And there are some interesting things that we notice, such as you can't just use one kind of data if you want good performance across the range of interventions. Here we see that to predict ventilation, whether somebody needs to be invasively ventilated, it's really these physiological measurements that make the most sense. But if you want to predict the need for a fluid bolus, you really need to take the notes and turn them into topics, and that helps you more. We also are able to look at things like convolutional filters and say, what is it that seems to be highly activating in a patient's trajectory for needing a ventilation? Why do we seem to predict that somebody needs to be ventilated? And those are patients here in red on average that have higher diastolic blood pressure, heart rates, and respiratory rates, but lower oxygen saturation. So they're hyperventilating. They're trying to breathe really, really quickly. Their respiratory rate is up, their heart rate's up, but that oxygen isn't getting to their body systems, which makes sense. And it's not just me who does research like this. Importantly, there's a huge community. There was a wonderful paper by Eric Topol a few years ago that benchmarked a bunch of papers. And these are all, every line is a demonstration of a machine learning system that performs at or above humans across the range of tasks in a human lifespan. And so the two things I want you to notice from this slide, because hopefully right now you're very impressed, are the sample size N across the prediction task varies from a couple hundred to several 100,000. And the AUC performance, which varies from 0.5 to 1 being the best, which never happens, also varies. And it's one number, a single number for all of the patients in the data set. And so you might ask yourself, as some of my students have, or I have, okay, do any of the patients in this sample look like me? And also, if there is a subset of patients in there that looks like me in some way, they're from the same genetic background, they have the same comorbidities, they're the same gender, what is their performance within this larger number that is aggregating over everyone? You might wonder that because AI is learning from human practice, and humans are imperfect. And so we're not just, when we take this hospital EHR and learn how to mimic doctors, we're not just learning from the very best performance that every doctor has ever had. We're learning from all of the records. It's very difficult to figure out if there are records that maybe we would not want to learn from. Those aren't annotated anywhere. And so what are we learning when we learn from human practice? Let's take an example. So it's very common, you may have heard, or maybe if you've read the news, to train machine learning models that learn on medical images, things like chest x-rays, to predict something important, like a diagnosis. They're the most often kind of cleared AI device by the FDA in the United States. And really, there's been a lot of work to try to do these kinds of models in an effort to support radiologists in generating notes, making diagnoses, maybe in situations where there are fewer radiologists available, like a rural setting. So we took the 3 largest chest X-ray data sets that are publicly available. That's over 700,000 images, good sample size. We trained a dense net, that's a kind of convolutional neural network, to predict a no finding label. That means the model says the patient is healthy. And then we're going to compare the false positive rate in different subpopulations. Here, by the reported sex and self-reported race of the patient. Why are we doing that? We're doing that because if you falsely positively predict that a patient is healthy more often on one subgroup, say female patients, that would lead to a higher rate of no treatment for those patients if you deploy the model, because it would falsely positively say, oh, these women are healthy, send them home, when actually they have a disease. So we train the model, get state-of-the-art results on average in predicting the outcomes as good or better than every other paper we found. And then when we examine the subpopulation false positive rate, we find there is the largest underdiagnosis in female patients, in young patients, in Black patients, and in Medicaid insurance patients. And intersectional identities like Black or Hispanic female patients are often underdiagnosed even more heavily than their aggregated group. So that would be then female patients on average, or then the majority group within female patients, like white female patients. And you might say, okay, fine, you made this point. Can't we just audit fairness in the predictive model? So maybe the thing that we should do here is very simple. Every time we train a model, we should report subgroup performance here, maybe by self-reported ethnicity, by the insurance type, or by the patient's reported gender. But sometimes it is not so simple to evaluate a model, because we're dealing with models that have learned on lots and lots of human-generated data that has very subtle proxies. What do I mean by subtle proxies? This is a contextual language model called SciBERT. Okay, SciBERT was trained on public scientific article abstracts. So this is PubMed, where you can go and search for any scientific article that's been archived there. And people have trained these contextual language models. Maybe you've heard of them. They're called transformers, contextual language models. Some people call them foundation models. So we took the one that is trained on good things, scientific articles, not Reddit or 4chan or something bad. And then we gave it a real prompt from a real medical record from a real hospital here in the Boston area, where I blank out race. This is, somebody's actual race was reported there. And then I asked the model to fill in the blank. This is a realistic task for models like these. People use them now. Famously, the NHS hired Babylon Health to make a chatbot that used a BERT-style model to do the very same thing. A lot of Google search is done this way. People screen resumes in this way. There's been suggestions you should do note infilling this way. And so if I put Caucasian or white patient became belligerent and violent, the model fills in the rest of the note with they were sent to the hospital. If I put African, African-American, or Black, then the model says that the patient was sent to prison. This is not something that would be easily identifiable in a simple audit. And so when we're using machine learning models, we have to be really careful about how we think about the perpetuation of biases that are present in actual health data right now. And this is not something that can be fixed by simply balancing data later. So we ran a study earlier this year, published in iClear, machine learning conference, which found that if you have bias at some point way in the past in data and make some nice embedding space, some model, and you release that model to people, and then people come along later and have perfectly fair data, perfectly balanced training data. But they still project that training data onto this representation that was learned with biased data initially. The model never recovers. It's never able to perform fairly in the subgroup. There's always a gap in performance because biased embeddings impact downstream tasks, even with rebalancing. So this is something we have to think about right now. Because bias is part of the clinical landscape. And you might think, I'm worried AI will kill me in the future. But what if the reason it might kill you in the future is because doctors are killing us right now? And we know that doctors are humans and humans are biased. And so a lot of the flaws that we see in clinical data reflect the biases that are present in society. So pop quiz number 1, let's see how bad this could be. Can you tell whether this note is from a Black or white patient? I manually removed all of the mentions of the patient's race from this note, so you can't actually see it. But can you see any clues about why this would be there? So you probably can't, because the doctors we surveyed could not, but the model can. And so some of these things make sense. Like, for example, in this patient population, we have a higher level of dialysis and hypertension and diabetes and other comorbidities in the Black population. But this is not something that you need a fancy language model to figure out. We were able to predict patient self-reported race in very large patient cohorts in Boston and New York using very, very simple bag of words and logistic regression models. And also the words that are being used are not consistently comorbidity based. There are references to skin that are very popular for, or very powerful in the model for determining whether somebody is white, because clinicians actually don't write about the physical presentation of dermatological symptoms in darker skinned patients. It's a well-noted problem in dermatology. There's also weird differences in the way you refer to the next of kin or people who have care provisions in the patient record, where we found that married female patients, if they were white, were significantly more likely to have the word husband mentioned, significantly less likely for married Black female patients. And so some of this could be in the social epidemiology literature. We've noted that there's some people who believe that there are really negative interactions in general between African-American families and care staff, especially when we're talking about next of kin or end of life care. And so they omit talking about family members that have some import in making decisions at that time. Second pop quiz. How deep does this go? I just told you, and you maybe understand from looking at the data, that there are clues in the words that humans write. Maybe we're a little bit biased. Maybe some of that is also just the comorbidities are different. Maybe the medical knowledge is not caught up to being less racist about skincare, whatever it is. Is this patient Black? This is just a chest x-ray. How could you possibly tell that from a chest x-ray? And I should say we surveyed a bunch of radiologists and they can't. So you shouldn't feel bad if you can't. But AI models can. They can do it really well. They can do it really well in many different modalities, in medical images from different sites, from different countries, for different kinds of patients. And whereas before I went through and showed you some of the proxies, the spurious correlations that the model was using to actually figure out somebody's race, things like comorbidities or how you're talking about somebody's family. Here, it's not body mass index, it's not breast density, it's not bone density, and it's not disease distribution. It's none of those things. It's not the lower or higher part of the frequency spectrum specifically. In fact, even when you bandpass filter these images so that they don't really look like chest x-rays that much anymore, the model can still tell with very, very high accuracy what you self-report your race to be. This is not your genetic ancestry or anything like that. So please don't have any weird eugenics notions that come out of this work. This is probably because darker skinned people tend to self-report Black or African-American race more often. And melanin in a very robust way interferes with the frequency spectrum bounce back of medical imaging devices. Is that a problem by itself? No. Is it a problem that it is trivially obvious to AI what your self-reported race will be when often a radiologist doesn't have that information, so that potentially the doctor could be given bad advice for only the Black patients consistently, and they wouldn't know that? Yes. And it's a problem because we don't think about this in as robust a way right now. We have much more simple fixes. Things like, can we fix model gaps with explanations? I just showed you there's all these problems. We can just fix them by using these more simple explanations. And people who say this say, well, complex models are hard to understand. And so let's just put these post hoc fixes on to approximate what it would be in a linear way, and that's explainable. This is a whole subfield, I should say. It's not like a small niche group. Like there's a whole separate like explainable AI movement that I don't agree with. And I don't agree with it because post hoc explanation models that approximate black boxes, I don't think are the solution. And so we decided to audit them. So we took the most popular, and I mean, these are very popular, like Lyman Shop are used all the time. I read papers that use them all the time, over 8,000 citations just for the Lyme paper, and global explanation models. And so these function in slightly different ways, but essentially they're trying to fit some sort of post hoc explanation that will be more interpretable onto a black box model. And we want to measure the fairness of the local and global explanations and compare what happens when we go from something that's maybe a complex nonlinear decision boundary that can do disease classification for males and females into, for example, something that is a less complex decision boundary that may then have worse group specific explanations. We're going to measure it in two ways: the difference between average fidelity and worst case fidelity. Maybe on average, you do pretty well, like the overall fidelity is 95%, but that's because on men you do 98% and on women you do 80%. We're also going to measure the difference in average absolute fidelity across any given subgroups. And we're not just going to do this in a health setting, because this is not just a problem in health. So we're going to use the MIMIC data set and look at predicting mortality across men and women, which is something that is very common in the machine learning for health community. But we're also going to look at recidivism risk, where you're trying to predict a defendant's chance for reoffending, which is being used right now famously by judges when they make bail decisions across patient self-reported race, whether a student passes the bar exam, and then your income, which is often used as a proxy for whether you should get a loan. We find that there is a significant performance fidelity gap across subgroups for local and global explanation models. What that means is using the explanation makes the model more unfair. And the gap gets worse as you make it more and more explained, as you make the dimensions smaller and smaller. And this is something that is linked to, again, spurious information. Your minority group can be detected from representations. If you remove the group information, it reduces the gap, but it doesn't get rid of it completely. So now that I've scared you a little bit, what are some of the directions that we can go in? Let's say that we want to continue to plan care, but we want to do it responsibly. And we don't want to just train a really fancy neural network and then have to explain it. We want to train something that you can use in its original form. And so one thing we might try to do is train a decision support checklist. And these are really popular in medicine. There's lots of them, more than I can enumerate. And that's because a checklist is really easy to use, deploy, and verify. What I mean by that is I don't have to somehow integrate my AI model into your EHR. I can just print out a piece of paper that has a list of things that you can check off that helps you with decision support. And so the problem with those, the scores that we use right now, the checklists we use right now, is that they are developed by humans. They're developed by a consensus often of a panel of experts who come together and say, in our experience, based on what we've read, based on what we know. But there's been very good work recently that shows that all of those risk scores and models that have been developed based on these expert panel consensuses are really biased. And so they routinely, across the range of clinical focus areas, either over or undercorrect the risk for African Americans because they're biased. Humans made them, and we inject our own imperfect, unbiased knowledge. So we tried learning an optimal predictive checklist, where we form checklist creation as a kind of machine learning problem called the mixed integer programming problem. And we work to directly minimize the error. So create a checklist that performs optimally well based on the actual data that we saw in the hospital. And importantly, the nice thing about this is we can add problem-specific constraints. Doctors care maybe about the number of items in the checklist. I maybe care about the gap between false positive rates with male and female patients. So here's an example. Let's try to predict mortality, whether you'll die after I give you an intervention like CRRT. Continuous renal replacement therapy is something they give you in the ICU if everything else has kind of failed and it's sort of a Hail Mary treatment. It's very painful and it's very expensive. And there's huge variation in whether it's administered or not. Sometimes even between rounds changes. Like one doctor comes in, puts you on it. The next one's like, this won't help that person. They take you off it, which is not good. And so we want to predict this so that if, for example, there's a high risk that you'll die after you get CRRT, they offer you end of life comfort measures and you don't die on this treatment. And so the goal is to trigger a multidisciplinary consult where the care team is told, if you give this treatment at end of life, the patient's likely to die, consult with the patient and the patient's family and others in the hospital setting. However, it's very important that we ensure fairness across intersectional patients groups here, because you could imagine if we had a much higher false positive rate, we would just say, oh, don't give it to any Black patients. They'll all die after you try to treat them. It's not what we want. We trained our first checklist with no fairness constraints. Look at this beautiful checklist. We're going to predict mortality given CRRT if 3 or more of these items are checked. Do you see anything here that has to do with gender or race? No. Any proxies you can see? Any spurious correlation? Not really, right? The doctors couldn't when I trained this checklist and gave it to them. They said, it looks great. This checklist has a max false positive rate gap between Black women and white men of 54%. That's insanely high. And there's no obvious proxy here. When you add in fairness constraints, you can get a new checklist that has an improved false positive rate gap, but you'll notice that the overall performance reduces a little bit. And that's because there's no free lunch here. You can't squeeze water from a stone. The data we have is the data we have. It is often imperfect. It's our job to do what we can with it and audit as well as possible what kinds of decision support will work well for different subgroups. But until we get more robust, diverse data, we have to work with what we have. Which brings me to the last part, working with what we have. I have just shown you that AI models can be very biased, and it can happen in a sneaky way, which I hope convinces you that it is not unreasonable for me to assume that you could train an AI model that was biased against one subgroup and it maybe wouldn't be caught. Okay, let's see what happens when you use that model. Does biased AI affect high stakes decisions? So many of you may have used or volunteered for a mental health crisis line. I did when I was just out of college. You'll get a call summary like this. The emphasis on colored text is added for this talk. It's not that way when we give it to subjects. People volunteered to read through these call summaries or, that have been, we say, transcribed by a volunteer, and they have to make one decision. They have to decide whether to send emergency medical help to the caller's location or contact the police department for immediate assistance. And we train them ahead of time that there's no liability risk because professional help is going to the site no matter what. All they're doing is deciding which kind. And we also train them that the only reason they should contact the police department for immediate assistance is if there is a risk of violence. It's the only reason. Always default to medical help unless there's a risk of violence. And then we varied whether we said the person was African-American or Caucasian, and then Muslim or not. And some of our baseline participants just got this and made this decision. And then some of our participants were given some advice. And we allowed 2 models to give advice, an evil one that we trained to be biased. So it always tells you to call the cops on Muslim and Black people. And then an unbiased one that does not disproportionately tell you to call the cops on Muslim and Black people. And then we integrated the biased and unbiased models in 2 ways. By either giving the advice prescriptively. So the evil one would basically always say, in this situation, our AI model thinks you should call for police help if the person was Black or Muslim. The unbiased one did not do, did not disproportionately say that you should call the police on Black and Muslim people. And then we also allowed these two models to give advice in a descriptive setting, where we had them either in a biased or unbiased way give the factual predicate flag. Our AI system has flagged this call for risk of violence, or our AI system has not flagged this call for risk of violence. And then you make the same decision. Okay. So what we found is that at baseline, respondents are not more likely to call the police on Black and Muslim subjects. That's great. And this is in a cohort of 438 clinicians and 516 non-clinicians. So that means people are not evil at baseline. That's good. And this is despite their reported political beliefs, their stated attitudes towards policing, their occupation, their gender, their age. When you give biased prescriptive recommendations, everybody is much more likely to call the police on Black and Muslim people, not just clinicians, not just non-experts, both of them, which is really terrifying. Because when you give the same biased advice, same evil advice in the descriptive way, when you just give the factual flag, people don't follow it. They have the same original fair decision making. Why do I think that's scary? Because people don't study this. This is not something that's well known. And when I train AI models, I'm not thinking about this tiny difference in when I deploy my model, make sure it only ever shows you the information in this specific way, not in this other way. The framing really matters here. Clinicians and non-experts are blindly adhering to prescriptive AI recommendations, but not to the descriptive flags. And descriptive flags, can still be impactful, we're finding. So clinicians adhere to the unbiased ones, but not the biased ones. This entire talk, I hope, has convinced you that there are no simple fixes for ethical AI in health. It's an ongoing process. We need diverse data and diverse teams to think through the sources of bias in data that go through problem selection and data collection, how we should evaluate comprehensively in outcome definition and algorithm development, and understanding when we do post-deployment audits that not all gaps can be corrected. So we need to know what sort of gaps are clinically acceptable. If we can't have perfect models, we can still have useful models that can do something positive for society. I think in general, health, we found, lags other machine learning subfields in reproducibility. But this is something that can be fixed by our community continuing to release code and data openly so that our results are just as reproducible as those in computer vision, general machine learning, and natural language processing. And I hope I've convinced you that we shouldn't, use a simple shortcut, explain the models. We need to understand processes. The data sheets for data sets recommendation, or model cards for model reporting, using big picture tools to understand potential biases throughout the process, because we need to work towards data, model, and processes that are reproducible and transparent. This is work that has been done with my Healthy ML lab at MIT. Thank you for listening to my work on creating actionable insights in human health.
All righty. Thank you so much, Marzyeh. Very interesting. Let me see. If I see this correctly, we already have the first question, or this is a big one. Maybe my suggestion, Ebenezer, if you're okay, let's try to work our way through a few of those topics that Marzyeh brought to us, and then also touch on this XAI flawed question. But I guess if we anchor it a bit more with what we just saw, it maybe helps us to kick off the discussion and to base it a bit more. So maybe to start, or with what you ended, you had this nice graph from Irene's overview paper with these steps, and to my mind, a lot of the themes that came across in many of the papers that you showed today is around data, which, I mean, it's also not news, but that seems often to be the source of a lot of the troubles we have when we want to make sure that a model can be actually deployed. And the first question that I would have is, I mean, in addition to bias, what do you, I mean, there's maybe, what do you think about like this problem of anyway, categorizability, let's say? So what part of race, for example, as a category can be captured in a chest X-ray, right? But if you ask a social scientist, what is race, like describe this identity in some way, they would open up a whole kind of textbook and talk about it from like 10,000 perspectives. Like, what can we actually, because when we lock in this category with this modality, we already kind of have a super big bias baked in, because there's only so much information, right, that can be contained in this input. So, I mean, doesn't it start there? And like, what can we do about that before we even talk about subgroups, right?
I think that, you know, we are obviously auditing in categories where there is very well established social science research demonstrating that there are disparities in care. So we're not trying to create categories or understand them on the fly, which is a whole separate area of research, actually, like figuring out, you know, where there are subgroups where there might not be previously known subgroups, right? So there's, you know, maybe subcategories of people who are treated differently for whatever reason. So in this work and all the work I've shown, none of it is trying to identify people who may be mistreated for whatever reason. We're doing these audits along predefined axes where people have noted that there are gaps in care. So specifically in Black patients and female patients and patients on public insurance. So that's sort of, I think, the context to view this within. I think it's a very important question to ask. You know, what is race? It's different for the two different papers, right? So the two pop quiz papers that I previewed for you. For the first one, your self-reported race is the way you identify, and it's probably reflecting the way that society sees you, and society is biased. And so your care team is interacting with you as a Black man, as a white woman, as a, you know, whatever those categories are, right? Like your care team is dealing with you that way. And that colors, funny choice of word, but that influences the way that they write your note. And that makes sense, right? There's a lot of social science research that really is supportive of this idea in general. It's very pervasive, right? The biggest thing that we found from that study is that when you remove self-reported race from the note directly, humans can't tell the race of this person anymore. They can't pick up on those tiny little subtle cues and guess, but AI can. Right? It's like, well, I looked at 1 million of these records and you always write about African-Americans this way, right? So I think that's one of the, you know, it's maybe not surprising that you can determine it. I think it is surprising that it's so trivially obvious with these little identifiers in a way that it is not to any of the doctors that we surveyed. They were really bad at this. But again, at least that makes sense, right? Like we are social people, we identify a certain way, and then society interacts with us in that way. The chest X-ray paper is very different, right? This is saying there's something about, and our theory is that it's actually just melanin, right? Like there's something about people, we believe, with darker skin that is interfering subtly with the spectrum bounce back in medical imaging in a way that it's not noticeable at all to any human expert trying to extract any clinical feature. It's tiny, right? But the AI model is like, of course, you can't see that. I see that. And again, that's only really problematic. You know, who cares if the AI can tell how you will, you know, is very good at telling how you will self-report your race? Why does that matter? It matters because when you get a radiology report, often you just get the chest X-ray and maybe a little bit about presentation, 32-year-old male, shortness of breath, evaluate for blah, right? They don't usually mention the race. And so again, like if we're thinking about a setting where there's biased models that are able to give you advice, one would hope that you would maybe notice that consistently told you to do something weird in all the Black patients, but what if that's not information that you have access to routinely, but the model knows it perfectly? And so I think that a lot of the questions that I ask are just asking us to explore, the current system that we have, the healthcare system that we have, as it's currently practiced, is not great, right? Like, it is what it is. And we're training AI models now to help support that and improve it, which I'm a big fan of, right? I continue to do this work. This is a space that I'm in. But we have to be very careful about how we do that, because it's not like this is a setting like tagging dogs in images, right? Where you could take any person from anywhere with any education level, speaking any language, and tell them, put a box around the dogs. And they're like, okay, I can put a box around a dog, right? This is a situation where two doctors can have gone to the same medical school and have the same expertise and be practicing for 2 decades, and they're allowed to disagree about your diagnosis. And neither of them is wrong, right? It's a very complex setting.
Yeah, I mean, I think the one stage we just talked about deals with, on the one hand, understanding those categories and also the limitations in the form they come when they are consumed by a machine learning model. Maybe another, at least what I understand to be one of the purposes of audits, or the type of work that you do with your team, is to detect those failure modes, let's call them. So if we have those, right, like subgroup performance gaps or even intersectional performance gaps. And maybe this is a moment to like pick up this question by Ebenezer, so about XAI. And to me, the reading race paper is a really good case in point, where basically you are confronted with an interesting phenomenon about the machine learning model, and you're like, okay, let's use XAI to find out what's going on. And you're not really learn a lot. At least I think that's right. That's the impression I got from the XAI experiments. You get really foggy heat map, but you don't really know much more than you knew before you did the experiment. And I mean, to me, one of the issues seems to be also in perspective. So understanding from a human point of view versus understanding also what you said, right? The model finds some signal, and it doesn't care whether this is human understandable or not.
Yeah.
And, right. Like, where do you see, like, if does it have a place? And is it an issue of perspective? Is it an issue of methods? Where do you see the main problem?
I think it's an issue of perspective. So I think that AI optimizes exactly what you tell it to. It'll use anything it can that's present in the image or the text or the tabular data, whether you want it to or not, whether you're aware it could even do that or not, to optimize the thing you told it to. You asked me to predict this. Okay, I'll use what I can to do that. That's what I'm being trained to do. I think that there's a really good literature now, and some of my students are working in this space on trying to remove spurious correlations, remove the undesirable proxy information that that models might use to learn and people would not have available to them or would not be aware that they could use. So that's a whole focus area in general, which is very interesting, right? Of like making sure that what we do is actually going to be generalizable. It's not suffering from spurious correlations. I think that explainable AI methods have a strong place there, where you look at during model development, you as a researcher, you look at, where is the weight of this model focused? Can I remove this particular thing and see what happens? Can I look at local projections, many of them, and understand how that varies? I think that that's fantastic. I don't think it should be used as a way to make models trustworthy. I don't think it should be used to deliver information to people, to end users. A lot of the really good explainable AI research that I have seen in the robotics community implies or, just directly shows that actually when you explain something, people trust it more even when it's wrong. There's really good research on that. That when you explain models in a way that it's like, even if it's not what the model actually looked at, right? If the model looked at feature A, but it's allowed to lie and say, I looked at feature B, people are like, oh, that makes so much sense, model. I believe you. And this is for things that are not health related. It's like, there was a great paper, I think in CHI last year, the ACM CHI conference, Hannah Wallach and team, and they were looking at estimating housing prices in the New York rental market. Which New Yorkers should be really good at doing, right? Like it's a big thing and they are really good at doing it until you let them see the recommendation of an explainable AI model, simple AI model. They go crazy and start listening to it and say that, oh yeah, a 5-bathroom, 2-bed would go for a lot, just like a 5-bedroom, 2-bath. And it's like, they catch that error when a black box AI model tells them that. They're like, no, stupid, that's obviously not true. And they also don't make that error when you don't give them any advice. But when you give them this advice that's like, the model says that there's lots of rooms and it goes square footage, they're like, that sort of makes sense. It's really terrifying because, as we showed, like clinicians and non-clinicians are really prone to this kind of anchoring and over trusting of things that they think are accessible to them, that they can understand. So that's my beef with explainable AI.
Understood. I mean, it seems to me maybe that one of the issues there is also a lack of interfaces between the let's say the view of the model. So the model doesn't care maybe about, if you don't regularize it during training to conceptualize or to learn a latent representation in a certain way so that you can interface it with human understandable concepts. So like to say there's some space where you cluster certain medical concepts in the latent representation or things like that, that there is just no naive way to understand the representation the model has of the input. And on the other hand, as you pointed out, humans tend to have this appreciation for some type of narrative or story, or if you give them some story to it, it makes them become makes the whole thing become more credible. So it seems to me the one of the issues is this type of interface. Similar, you had this one work on these the metric deep paper from iClear.
Yeah.
Where I feel like this is maybe a direction that could be very promising, where you meet the model on its own terms. So you have those representations and you see what can you do with that, right? Whether you retrain the whole backbone or just the head, right? But that seems maybe a bit more plausible and also reduces the risk for this anthropomorphic kind of, okay, this makes sense because I think this is how it could be. But it's a complicated one.
I think that's one of my favorite papers actually, because it was inspired by a question, right? So somebody asked me a question when I was on a panel. They said there's some data, like the Veterans Affairs data, the VA data, it's very large, right? But is inherently biased. Only 6% of the veterans data is female. And there was a really great paper that came out like 4 or 5 years ago now about estimating acute kidney injury from this data. And then during the pandemic, there was a legitimate question of whether we could take that model. You can't access the VA data, right? Like it's very private. Like you have to sacrifice a goat in order to like get anywhere near it. But the models, maybe you could just release those representations. And then, during COVID, a lot of people were getting acute kidney injury, men and women, right? It would be really nice if we could run that model and figure out, who is more prone to getting AKI during the pandemic. And so there was a legitimate question that was asked, do you think it's okay for us to rerun these models using this representation that thankfully was trained on millions and millions of people from the VA? We have, a few thousand now, it's balanced, men and women. Will this work? And I had no idea. I just didn't know, right? I was like, I really don't know. We need to run that experiment. We need to figure that out. And it turns out you can't. There are ways, we talk about this in the paper, to force the model to try to decorrelate these sensitive attributes partially. So in the paper, we looked at face identification, and we tried to force it to learn a good representation for both Black and white faces. We also looked at the birds data set, where we tried to force it to learn a good representation for birds despite different colors of their feathers. It's not perfect, though. It's a strong, spurious correlation, and it learns it, right? It's a shortcut. Humans use shortcuts all the time, but we're bombarded with all of this, counterfactual evidence that hopefully encourages us not to make gross generalizations about the other people we know or systems. Models don't just sample from the world. They see the data we give them. And then we're surprised when they do weird things or things that we don't really like about our society as it is, right? We believe that they should provide, health recommendations that are equitable, but we don't do that now. How are they supposed to do that with the data we're giving them?
Yeah, that's a good point. And it's also, it's a really hard nut to crack, or also to just wrap the head around. Because in addition, I think to it feels sometimes this discourse and around reliability and whether we call it trustworthiness, particularly in machine learning for health, because it's such a sensitive application domain. It's really difficult also because it's such a complex system. So you can basically, for one problem, you have to find an answer from 5 different perspectives, right? So the ML person can say something about, okay, this is what we can do with the representations. And then if you have somebody running a clinical trial, they have something to say about, okay, what is the population that we are going to run this trial on? Who is in the hospital, who is the patient population in the hospital that this is going to be used at? So it's kind of, it seems really challenging to combine all those different groups to pull in the same direction. And I mean, this would be kind of my larger question to you for closing. So if we all agree that we want reliability, and we agree that machine learning can have a place in improving patient outcomes. So if this is the kind of working assumption, and we don't want inequities or certain biases, but we only have a limited energy budget, right, to attack these things. So where do you see how should we spread or invest this energy? Is it more like on the structural side of things that you also talked about, where the data that feeds into the ML systems, this is where we have issues, how care is delivered, and before we kind of don't fix these things, there is no really way to go beyond a certain quality threshold with the ML models? Or is there directions? I mean, I know Harun, he showed me this poster a few weeks ago at SAIL with a checklist, and I haven't seen, I think, this type of work in a while, and it's so obvious and obviously or useful for a clinician, because okay, you just get a checklist, right, and this you can use, and you have those constraints met or not met. And I mean, is this the direction, right? Do we have to maybe adjust a bit the way we do machine learning, and also the kind of product that can come out of machine learning, so that it has the utility? So these two axes are there: the structural side of things, revolution, change society, and the technical side of things, right? Like, okay, let's push models, let's rethink how we approach machine learning in the space. Where do you think we have to invest this limited energy budget that we have as a community?
I think we actually have a big energy budget. I feel like the community is huge, which is great. There's not just there's SAIL, the conference that you mentioned. There's CHILL, ML4H, MLHC. Every single one of the mainstream machine learning conferences now has like a health application area. There are separate journals like Lancet Digital Health, Nature Digital Medicine that are just supposed to be about using machine learning to do interesting things in health. And so I think that our budget is getting larger. And I think that the two things, or maybe three things, if I could have three things, the three things I think we need to invest in is better data, because the data is very bad. And that has informed some of our very poor medical practice right now. I think improving data and the way that the All of Us data set has, where they've worked very hard to get a representative and diverse sample, that's really valuable, very meaningful. Not just like, oh, it's quick and efficient to like get very rich, healthy, well-educated people to be in this sample. We need to actually know what's going on. And for that, we need a diverse data set. I think number two is creating methods like Karen did with the checklist that actually play into the way we know models are going to be used and need to be used, rather than saying, I made a thing and now I have to explain it and the explanation makes it worse. And, I think there's more innovation that can be done on that side. And then finally, we need to start doing these post-deployment audits. I mean, if a tiny change in the sentence you use makes that big of a difference, I want to know more. Why did I not know this? Why is this not just a well-established thing that is, on some FDA website? When you deploy a model in this setting, you must present the flags like this. Like, I would have liked to know that. I think that's an important thing that we as a community who are developing models that will likely be downloaded by somebody we don't know and deployed by somebody else we don't know, we should have as caveats even when we release our models.
All right. That seems like a good note to close on. So we should want to know more. But wait, now Marzyeh, since we were so engulfed in this discussion, I see there was another one that just came in from the audience. Let's use the last minute for that. So
I see this question, and I will tell you, I think synthetic and simulated data is not good. I think it works when you have well understood, well-defined data generating processes. That is not the situation that we are in with health data, in any health data that I am aware of, unless it's very small bespoke simulators for things like, here's an insulin to diabetic response model. So I don't use simulated or synthetic data for anything other than at the very beginning of model development, testing hypotheses about how a model should work in different conditions. I don't think it's a good way to work in this space, because synthetic data and simulated data often has to make gross generalizations. And by gross, I mean large, large generalizations or approximations to the data generating functions. Does that make sense? I'm not sure if we lost Luis or if we lost me.
Maybe. Well, not to me, he looks frozen, so we might have lost Luis.
That's okay. I will say thank you so much for inviting me.
Oh, it's a pleasure. Let's see if he can reconnect. Yep, he's reconnected. Hi, Luis.
Okay.
All right. Sorry for that. I was just kicked out while Marzyeh was answering. But we are out of time, if I see this correctly, right?
Mm-hmm.
Yeah.
All right, then Marzyeh, any last words, or have you already spoken?
No, I think the last thing about the synthetic data question is we wrote a paper at FACT last year called Can You Fake It Till You Make It? And it's showing that synthetic data actually does not work well in most of the settings that we evaluate, and some of them are not health settings. It retains bias that was present in the original data, and so you could be learning more biased representations because you tried to synthetically simulate your data. So that's it.
All right. Then, yeah, let's finish on time and thank Marzyeh again for taking the time. Thank you, everyone who took the time to listen, and also ITU, Julian, for hosting us. It was very smooth. And I understand there is a networking session happening on ITU side. So if any of the guests are interested to try that out, feel free to register. I'm sure Julian and colleagues will lead you the way. And yeah, Marzyeh, thank you. Wish you guys all a
Thank you.
happy
Take care, everyone. Bye.
Bye-bye.
AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. After the networking session, we invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for Good.